We gaze at the stars, marveling at the vastness of the cosmos. But do you ever wonder where chemical phenomena are crucial in our daily lives? Today, we're diving into the world of naming ions. These tiny charged particles play a massive role in the world around us. Ions are everywhere in chemistry. They're like the building blocks of many compounds. From the salt in your kitchen to the batteries in your gadgets, ions are integral to countless substances and processes. But what exactly are they? Let's break it down. Ions are atoms or groups of atoms that carry an electrical charge. This charge is due to an imbalance between the number of protons and electrons. This charge comes from having either more electrons, negative charge, or fewer electrons, positive charge, than protons. It's all about the balance of these subatomic particles. Think of it like this. Electrons are like tiny negative particles, and protons are like tiny positive particles. When the numbers of these particles are equal, the atom is neutral. Or if an atom has the same number of protons and electrons, it's neutral. But this balance can change. But when it gains or loses electrons, it becomes an ion. This process can happen through various chemical reactions or physical processes. Positive ions are called cations, and negative ions are called anions. Cations have more protons than electrons, giving them a positive charge, while anions have more electrons than protons, resulting in a negative charge. These charged particles are super important. They are fundamental to the conduction of electricity, the formation of compounds, and even the functioning of our bodies. They play key roles in everything from electricity to chemical reactions. For instance, in an electrical circuit, ions help conduct current, and in chemical reactions, they can drive the process forward. If you are interested, I made a video explaining the topic in more detail. Make sure to check it out here. So, understanding how to name them is crucial. Knowing the difference between cations and anions and how they interact is foundational knowledge for anyone interested in chemistry. As you delve deeper into chemistry, you'll see how ions form bonds to create compounds, participate in reactions, and even influence the properties of materials. The world of ions is vast and fascinating, and it's just the beginning of your journey into the microscopic world. Let's start with polyatomic ions. These fascinating entities are crucial in the world of chemistry, and understanding them can unlock many doors in your scientific journey. These are groups of atoms that act as a single unit and carry an overall charge. They are like a tightly knit team, each atom playing a specific role to maintain the stability and functionality of the ion. Think of them as a team of atoms working together. Just like a sports team where each player has a position and a role, each atom in a polyatomic ion contributes to the overall charge and structure. One example is the ammonium ion, NH4+. This ion is quite common and plays a significant role in various chemical reactions, especially in biological systems. It has one nitrogen atom and 4 hydrogen atoms bonded together, carrying a positive charge. This positive charge is due to the loss of one electron, turning the ion positively charged. Another common one is the carbonate ion, CO3 2-, with 1 carbon and 3 oxygen atoms, carrying a -2 charge. This ion is essential in geological processes and is a key component of many minerals. Remembering the names and formulas of these polyatomic ions is important. They are frequently encountered in both academic and practical chemistry, so having a good grasp of them is beneficial. My professor allowed us a list of the polyatomic ions on our exams, especially for the first Gen Chem classes. It just all depends on your professor. Honestly, I would verify just to be sure. Nothing can describe the feeling of showing up to the exam, expecting all the formulas to be on the cheat sheet, only to be empty out of no formulas. At that point, you can't answer any questions, because you relied heavily on the equations being there. I may or may not be talking from personal experience there. The ion list pops up frequently in chemistry. Whether you're balancing chemical equations, understanding reaction mechanisms, or studying biochemical pathways, polyatomic ions are everywhere. Luckily, there are some patterns and tricks to help you memorize them. Mnemonics, flashcards, and repetitive practice can make the task much easier and more enjoyable. For instance, many polyatomic ions containing oxygen, called oxyanions, end in "ate" or "it." These suffixes can give you a clue about the number of oxygen atoms present in the ion. The "ate" ending usually indicates more oxygen atoms than the "it" ending. For example, nitrate, NO3, has more oxygen atoms than nitrite, NO2. Keep practicing, and you'll be a pro at recognizing and naming these teamwork ions in no time. With consistent effort and the right study techniques, mastering polyatomic ions can be an achievable and rewarding goal. Enjoying the video so far? Subscribe so that you ace that chemistry class. Or if you like learning about chemistry for fun, regardless of why you clicked on this video, subscribe so you never miss any future ones. I will provide a link to the textbook down in the description below. This textbook is the source of all my videos and lectures, and where the information comes from for my general chemistry videos. Let's get back to the lecture. Now, let's move on to monatomic anions. These are simple ions formed from a single nonmetal atom that has gained electrons. They're like solo artists in the world of ions. Naming them is pretty straightforward. We take the stem of the element's name and add the suffix, id. For example, chlorine, Cl, becomes chloride, Cl negative. Oxygen, O, becomes oxide, O2 negative. And nitrogen, N, becomes nitride, N3 negative. It's like giving the element a new last name to show it's now a negative ion. Remember, anions are attracted to positive charges, just like the negative end of a magnet is attracted to the positive end of another magnet. Monatomic cations with one charge, with straightforward naming. Next up, we have monatomic cations with a single ionic charge. These are positive ions formed from a single metal atom that has lost electrons. Just like the monatomic anions, they're also like solo artists, but with a positive vibe. Naming these cations is a breeze. We simply use the element's name followed by the word ion. For instance, sodium, Na, becomes sodium ion, Na+, calcium, Ca, becomes calcium ion, Ca2+, and zinc, Zn, becomes zinc ion, Zn2+. It's important to remember that the charge is written as a superscript after the ion's symbol. This helps us keep track of the electrical charge. Monatomic cations with multiple charges, a naming challenge. This delves into the complexities of naming ions that can have more than one possible charge, a common occurrence with transition metals. Now, things get a little trickier with monatomic cations that can form multiple ionic charges. Unlike simpler ions, these cations can lose different numbers of electrons, leading to various charges. Some transition metals are like chameleons, able to lose different numbers of electrons depending on the situation. This adaptability makes them versatile, but also complicates their naming. To avoid confusion, we have two ways to name these ions: the stock system, using Roman numerals, and the classical system, using suffixes. Each system has its own set of rules and applications. In the stock system, we write the element's name followed by a Roman numeral in parentheses to indicate the charge. This method is straightforward and widely used in modern chemistry. For example, iron, Fe, can form Fe2+ and Fe3+ ions. These different charges result from iron losing either 2 or 3 electrons. These would be named iron 2 ion and iron 3 ion respectively. The Roman numeral clearly indicates the specific charge of the ion, making it easy to understand. The classical system uses the Latin root of the element's name followed by either OUS for the lower charge or IC for the higher charge. This method has historical significance and is still used in certain contexts. So Fe2+ would be ferrous ion and Fe3+ would be ferric ion. The suffixes OUS and IC help distinguish between the different charges in a more traditional manner. While the stock system is generally preferred, it's helpful to be familiar with both naming conventions. Understanding both systems allows for greater flexibility and comprehension in various chemical contexts. In academic settings, you might encounter both naming systems, so it's crucial to recognize and understand them. This knowledge will aid in reading scientific literature and communicating with other chemists. Mastering the naming of monatomic cations with multiple charges is important in chemistry. It not only helps in identifying compounds, but also in predicting their behavior in reactions. You'll find that these naming conventions are just the beginning. They form the foundation for more advanced topics and applications in the field. So whether you're using the stock system or the classical system, remember that each has its place and purpose. Both systems contribute to the rich language of chemistry, helping us describe and understand the world at the atomic level. Keep practicing these naming conventions, and soon, you'll find them second nature. With time and experience, you'll be able to navigate the complexities of chemical nomenclature with ease. And that concludes our monatomic cations with multiple charges. Oxyanions of halogens, oxygen's influence. Lastly, let's explore oxyanions of halogens. Halogens are a group of reactive nonmetals like fluorine, chlorine, bromine, and iodine. When these elements combine with oxygen, they form oxyanions with specific prefixes and suffixes. The number of oxygen atoms determines the name. If there's only one oxygen, we use the prefix hypo and the suffix it. For example, clo is hypochlorite. 2 oxygen atoms get the it suffix, like ClO2 chlorite. 3 oxygen atoms get the ate suffix, like ClO3 chlorate. And finally, 4 oxygen atoms get the prefix per and the suffix ate, like ClO4 perchlorate. See the pattern? It's like a code to decipher the composition of these oxygen-containing ions. Bringing it all together, mastering ion naming. Congratulations! You've journeyed through the world of ions and hopefully learned how to name them. From simple monatomic ions to complex oxyanions, you can now identify these charged particles like a pro. Remember, ions are essential for understanding various chemical processes. Mastering their names and formulas will undoubtedly strengthen your chemistry foundation. Keep practicing, and soon you'll be fluent in the language of ions. Happy experimenting! Like and subscribe. Make sure to share if you found this video useful. Be sure to have a nice night, and good night.